Yo, Tech Wizards! Welcome back to the Baz AI YouTube channel, where we rip apart complex tech architectures with confidence, clarity, and a whole lot of geeky enthusiasm. Today, we're diving into the architecture of LLMD, a beast of a platform for generative AI at scale. As detailed if you're into AI, Kubernetes, and cutting-edge inference tech, this is your jam. Smash that subscribe button, hit the bell, and let's unpack this layered architecture with technical precision to fuel your inner nerd. The LLMD platform is a powerhouse for large language model (LLM) inference, built on a layered architecture that leverages industry-standard, open-source technologies like vLLM, Kubernetes, and an Inference Gateway. This isn't just another AI stack, it's a meticulously engineered solution for scalable, efficient, and resilient generative AI workloads. Let's break it down layer by layer, diving deep into each component with domain-specific rigor and zero fluff. What is LLMD? The big picture. LLMD is a Kubernetes-native platform designed to deliver high-performance LLM inference at scale. It combines vLLM for optimized model execution, Kubernetes for orchestration, and an inference gateway for traffic management, creating a robust ecosystem for deploying generative AI applications. Think of it as a turbocharged engine for LLMs, enabling everything from chatbots to complex reasoning tasks with low latency and high throughput. Let's dissect the architecture to see how it achieves this. Layered architecture of LLMD. The LLMD architecture is structured as a layered stack, each layer purpose-built to handle specific aspects of LLM inference. Below, we'll explore each layer with technical depth, using industry-standard terminology to ensure clarity. 1. vLLM layer, optimized LLM inference. At the core of LLMD is vLLM, an open-source library designed for high-throughput, low-latency LLM inference. This is the execution engine that runs the actual language models. Here's the technical breakdown. Paged attention. vLLM introduces paged attention, a novel memory management technique that optimizes GPU memory usage by paging key value, KV caches. Unlike traditional attention mechanisms that store entire KV caches in GPU memory, paged attention dynamically pages cache data, reducing memory fragmentation and enabling larger models or higher batch sizes without OOM errors. Continuous batching. vLLM implements continuous batching to maximize GPU utilization. Instead of processing requests in fixed batches, it dynamically groups incoming requests, minimizing idle time and boosting throughput by up to 24x compared to traditional inference frameworks. Model parallelism. For massive LLMs, vLLM supports tensor parallelism and pipeline parallelism, distributing model weights and computations across multiple GPUs. This ensures scalability for models with billions of parameters. Supported models. vLLM is compatible with popular LLMs like Llama, Mistral, and GPT-style architectures, making it versatile for diverse generative AI workloads. vLLM is the muscle of LLMD, delivering blazing fast inference while keeping resource usage lean. It's the foundation that makes large-scale LLM deployment feasible. 2. Kubernetes Layer, orchestration and scalability. The Kubernetes layer is the orchestration backbone, providing scalability, fault tolerance, and resource management for LLMD. Kubernetes ensures that the vLLM inference workloads run smoothly in a distributed environment. Here's how it works. Containerized workloads. Each vLLM instance runs in a Kubernetes pod, containerized using Docker. This ensures portability and isolation, allowing LLMD to deploy models across heterogeneous hardware, e.g., NVIDIA GPUs, AMD ROCm. Horizontal pod autoscaling. HPA Kubernetes HPA dynamically scales the number of vLLM pods based on metrics like CPU/GPU utilization or request latency. This ensures LLMD handles traffic spikes without over-provisioning resources. Custom Resource Definitions. CRDs. LLMD extends Kubernetes with CRDs like Inference Service, which define model-specific configurations, e.g., model type, batch size, quantization. These CRDs allow declarative management of inference workloads, aligning with Kubernetes GitOps philosophy. Multi-cluster support. For global deployments, LLMD leverages Kubernetes federation capabilities to distribute inference workloads across multiple clusters, ensuring low-latency access for geographically dispersed users. Kubernetes brings cloud-native resilience to LLMD, making it a scalable and fault-tolerant platform for production-grade AI. 3. Inference Gateway, traffic management and security. The Inference Gateway is the entry point for all requests, acting as the control plane for traffic routing, security, and observability. Built on industry-standard API gateway patterns, likely inspired by tools like Envoy or Nginx, ensures efficient and secure request handling. Let's dive into its features. Request routing. The gateway uses path-based or header-based routing to direct requests to the appropriate vLLM pod. For example, a request to /chat might route to a conversational model, while /translate hits a translation-optimized LLM. Load balancing. The gateway implements weighted round-robin or least connection load balancing to distribute traffic across vLLM pods, optimizing for latency and throughput. Security policies. The gateway enforces TLS termination for secure communication, using Kubernetes secret resources to manage certificates. It also supports authentication, e.g. OAuth2, JWT, and authorization via role-based access control, RBAC, or Open Policy Agent, OPA. Rate limiting and throttling. To prevent abuse, the gateway applies rate limits, e.g. 1,000 requests/minute per client, and throttling policies, ensuring fair resource allocation. Observability. Integrated with tools like Prometheus and Grafana, the gateway exposes metrics on request latency, error rates, and throughput, enabling real-time monitoring and debugging. The Inference Gateway is the gatekeeper, ensuring requests are routed efficiently while maintaining security and observability. 4. Integration with observability and storage. LLMD Architecture integrates seamlessly with observability and storage systems to support production-grade operations. Observability. The platform leverages Prometheus for metrics collection, Grafana for visualization, and OpenTelemetry for distributed tracing. This provides end-to-end visibility into inference performance, from gateway latency to vLLM processing times. Storage. Model artifacts, e.g. weights configurations, are stored in a persistent volume managed by Kubernetes, often backed by cloud-native storage solutions like AWS S3 or MinIO. This ensures fast model loading and fault-tolerant storage. Logging. Centralized logging via Fluent or Loki captures detailed logs from vLLM and the Inference Gateway, aiding in debugging and compliance. These integrations make LLMD a production-ready platform, capable of handling enterprise-grade AI workloads. Why LLMD is a game-changer. LLMD Architecture is a masterclass in combining open-source technologies for maximum impact. vLLM delivers unparalleled inference performance, Kubernetes ensures scalability and resilience, and the Inference Gateway provides secure, efficient traffic management. Together, they create a platform that's not just fast but also flexible, secure, and ready for global-scale AI deployments. Whether you're building a chatbot, a code generator, or a reasoning engine, LLMD has the technical chops to make it happen. Call to action. That's the deep dive into LLMD Architecture. From vLLM's paged attention to Kubernetes CRDs and the Inference Gateway's robust traffic management, this platform is a beast for generative AI at scale. Want to see LLMD in action or explore more AI tech? And don't forget to subscribe to the Bazai YouTube channel for more tech breakdowns. Like, comment, and let me know what you want to dive into next. Let's keep the AI revolution rolling.